Hi, everybody. Good morning, and welcome to a lesson today on pedigrees. This is something that I really love teaching. It's something that I get pretty fired up about. If I ever asked you guys to draw out your family tree or your family pedigree, I'm sure that would be a really fun exercise for some of you. Some of you it would be a little bit more challenging because you have huge families. But today we're going to teach you the basics of how to read pedigrees and why they are so important to study as part of our genetics unit. So with pedigrees, the first thing to understand is what do all of the symbols on them mean? So I'm going to go through those with you. First ones are how we indicate if someone is male or female on the pedigree. So we use a square for males, a circle for females. And then if we don't know because it wasn't well recorded, for example, in my family history, I know I have an Irish ancestor that was simply called Frankie. I don't know if that was Francis or Francine. There's no way of telling. In addition, if somebody is unborn, so it's a baby and they haven't determined the gender yet, but we know that there is going to be a baby created, we would use that diamond symbol for them. Good way to remember it is that this system was designed by male scientists, and so they determined that females are curvy, so they did circles for females. When you're looking at a pedigree, you're going to see that some people on that pedigree are shaded in. They've got a dark circle or a dark square. This doesn't mean that that person is sick. They are not infected with something. It simply means that they are affected by a genetic trait. So maybe they are affected and they have brown hair. They are affected and they have green eyes. They are affected and they are colorblind, something like that. If we know that someone is a carrier, either through genetic testing or because of looking at all of their offspring, we know that they have to be a carrier for that trait. We shade in half of that shape. So as you can see, here we've got half the shape that is unaffected, half the shape that is affected. That simply means that this person looks like they don't have it, but they are passing it along to their children. There's also a lot of lines on a pedigree. The first type of line is directly connecting a circle and a square. We consider that a mating line. It used to be called a marriage line, but now we just call it a mating line. And then we have a sibship line. This is a horizontal line as well, and it doesn't directly connect a male and female. It's connecting you and your siblings. So here would be me, a sister if I had one, and a brother, showing that we are sharing the same parentage, but we are not mating. If there are twins created from that sibship line, you would simply just draw branching, showing that there were multiple births at the same time. Okay, so I'm sorry, one birth event, multiple children. So that would be twinship. You could do boy-girl twins like I've got here, identical girl twins, identical boy twins, triplets, same thing. One offshooting branch, lots of babies from that branch. If there is a case of inbreeding, which we see a lot in the royal families of Europe, also in very secluded communities in India, Pakistan, even certain faith groups like the Quakers in Pennsylvania, there could be some inbreeding in those populations. So if you are mating with a close relative, we do a double line to indicate that you are not only having a mating relationship, but that you also have a lot of common bloodlines, whether it's a first cousin or an uncle, aunt, that kind of thing. And then if somebody has multiple mates, so for example, if this is my Uncle Dave and he got married to my Aunt Deb, and then later they got divorced and he remarried to my Aunt Lisa, this would show that he has multiple mates with offspring. So if I was going to look at one of my favorite families in fiction, the Weasley family from Harry Potter, you can see that there's obviously a trait that is very common in the Weasley family. And just in case you didn't know anything about the Harry Potter books, that trait is their red hair and freckles. So if I was to look at this pedigree, very first thing that I would do is I'm going to mark circles and squares, males and females. And then I'm going to shade in those circles and squares that represent somebody who has this genetic trait of red hair. So that's how that would look. Everybody who had red hair is now shaded in because they are affected by that trait. All of my females are circles, and all of my males are squares. The next thing that I'm going to need to do is figure out how is this trait inherited? Is everybody getting it? Is it a dominant trait? Is it skipping generations? Is it a recessive trait? How am I going to figure that out? And the next thing I'm going to have to do is I'm going to have to label these people. Not everybody's going to know when I talk about Harry Potter. Of course, I would know because I'm a huge dork. They're not going to know about George and Angelina Johnson's son, Fred. They're going to think, oh my gosh, who is this nerd? How do they know this? So instead, we're going to label the generations with 1, 2, and 3 in Roman numerals, and then we're going to number the people across each row with just regular numbers. So generation 1 dash 1, that's Molly. Generation 1 dash 2, that's Arthur. That way you don't have to explain things like, oh, it's my second aunt's cousin's uncle. No, you just use the numbering system when you're doing that. There is a full-size copy of this document for you in Classroom. It's a PDF, and this is the guide that we're going to use to reading pedigrees. It's a flow chart. So you're going to ask 2 questions. Does it occur equally in males and females? And does it skip a generation? And based on your answer, yes or no, it'll tell you how that trait is inherited and what you're going to do with those individuals that have the trait. How are we going to label them to figure everything out? How are we going to figure out genotypes and phenotypes? So here is our guide, and here is our first practice pedigree. So on that first practice pedigree, you can see that we've got this woman up here, round as a female, that is affected by this trait, and then it seems to not appear for a while. And then way down at the bottom, we've got 2 kids that have it, a boy for this square and a circle, this girl. So let's look at our question. Does it occur equally in males and females? Yep, boys and girls are both getting this trait. So yes, our answer then is autosomal. This trait doesn't matter your gender, it's inherited equally in both. The next question that we're going to ask is, does it skip any generations? And my answer here is yes. There are 2 entire generations here where the trait doesn't show up at all. And then it shows up again. It's been hiding. It's been mysteriously hiding behind all of this stuff. If I need to double check, I can, but in general, the answer is yes. So that means that the trait is recessive. I'm going to highlight here. I forgot I had that. So it is autosomal. The answer is yes, it skips a generation. So it is an autosomal recessive trait. And right here in the box, it tells me that all affected individuals or all shaded in individuals are going to be little a, little a. And I can move this over. And all unaffected individuals have to have at least 1 copy of the dominant allele, big A. So for example, if this trait was talking about being albino in rats, those all-white rats with the freaky red eyes, it's really scary. If they have at least 1 big A, they made pigment and they're fine. They're a brown or a gray rat and they look normal for a rat. But if they got 2 copies of the albino allele, little a, then there's those freaky white rats with red eyes. They have no pigment. So that'd be this one, skip a couple generations, and then it showed up again way down here at the bottom. So how do I code that? Here, I'm going to write in what it said. All of those affected individuals are little a, little a. Everybody who's unaffected, we know, has to have at least 1 copy of big A, just like so. But how do I know what that second letter is? Well, my tip is start at the bottom and then work your way up. Try and track that backwards. So if we look down here at the bottom, this girl has 2 copies of little a, but her parents both have a copy of big A. How is that possible? It's possible if both parents are heterozygous. They are both big A, little a. They don't look albino, but they somehow passed it on. We know she had to get 1 from dad and 1 from mom. I can double check my work by looking here at a Punnett square. Is that possible for 2 parents who don't have the trait to pass it along? Yes, it is. If they are both heterozygous, this last box here on the Punnett square is going to show you that they could have a child who is homozygous recessive, little a, little a. So from there, I'm going to track back and find the rest of them. These kids, we know that they got their big A from dad. They had to get a little a from mom. So we can fill those in. Now, we do have 3 or 4 individuals here that we really don't know what their second allele is. We don't know if it's a big A or a little a. So, based on their kids, we can't tell. And then here, she married into the family. We have no idea what her second letter is. So for those individuals, we just write A dash, not A minus, A dash, because that second letter, we can't really tell based on the information that we've been given. Let's try another one. So here's my second pedigree. And as you can see, we've got a male, a female, 2 females here that are all affected by that trait. Let's see if I can move this. Yes, I can. For some reason, that last row is not showing up, so I'm going to pause for a second. Okay, I'm back. Sorry. Hopefully this fits a little bit better over here. So here's our second pedigree. You can see that we've got these people who are affected, and then way down at the bottom, I need to do this again. Way down here at the bottom, we've got 1 last person who's affected. So let's look at our questions. Question 1, does it occur equally in males and females? Yep, we've got girls and guys who are getting it, so that tells me it is autosomal. Second question, does it skip a generation? So if you look here, parent doesn't go to their children, parent goes to some of their kids, but not this one. These two parents do not have the trait, but somehow it showed up in their kid. So technically, yes, it does skip a generation. Even though there is an affected individual in the grandparents, affected individuals here with these two aunts, it doesn't occur in the parents. It skips them, but then it shows up again in their kids. So the answer is yes, it does skip a generation. So that tells me that this is recessive, autosomal recessive. So that tells me what to do. It says all affected or shaded in individuals are little a again. And all of the unaffected individuals have at least one copy of big A. That's why they didn't get this trait. So let's go ahead and fill in all of the affected individuals. And then all of the unaffected individuals have to have at least one copy of big A. Now I've already pre-filled all of these in, but let's figure out how I got that answer. Once again, down here at the very bottom, this guy is little a, little a. Both of his parents have to have a big A because they're not shaded in, but we know that he had to get one big A from mom, or I'm sorry, one little a from mom, his other little a from dad. That's how we figured out that section. Over here, we know that these kids have to be heterozygous. They had to get a little a from mom, and then they got a big A from their dad because they aren't sick. These two girls got a little a from mom. They had to get their second little a from dad. That whole law of segregation, you get one trait from each parent because of sperm and eggs and all that stuff. So you got one little a from mom. The other little a had to come from dad. You can't get both of them from mom, okay? And then over here, we've got on this side, we know all of these children, dad and all of his sisters and brother, they have to be big A, little a. They had to get a little a from dad. They all got a big A from mom because none of them are shaded in. But way up here, we have an A dash. We really don't know. It's probable that she's big A, since none of the kids got this trait, but we don't know for sure. So we're going to leave that as A dash. And then down here at the bottom, we know that these two kids are A dash because they got a big A from dad. And then from mom, they could have had the big A or the little a. We don't know if they're homozygous dominant or if they're heterozygous. Let's do the next one here. So once again, my first question is, does it occur in males and females? I'm going to shrink this video down just a little bit. Does it occur equally in males and females? Yep, I've got guys, the squares, and girls, the circles, who are both getting this trait. So it's going to tell me, yep, it's autosomal. Second question, does it ever skip a generation? Let's see, parent to child, parent to child, parent to child. So this one, probably not, but I'm not 100% sure. And then let's use the double check. Do I ever have a case where both parents are affected? Yeah, both of these guys are affected by the trait, and somehow they have a kid who is not affected right here and right here. The only way that that's possible is if this is a dominant trait. Here's my other double check. Every kid who is affected, do they have at least one affected parent? Yep, they can trace it to their parents, they can trace it to their parents. So that tells me that this trait is dominant. Let's look at that. All affected individuals have at least one copy of big A, and this time all of the unaffected individuals are little a, little a. So this is completely different than our first two practice problems. We flipped it because based on those questions, we know that this is a dominant trait. So if we look at that, we fill them all in. Everybody who's unaffected is little a, so all of the white circles and squares are little a, and this time everybody who's shaded has to have at least one copy of big A. Remember that that's the only way this part works. Big A, we know that, but somehow they ended up with a kid who doesn't have it, little a, little a. Let's track it back once again from the bottom, working our way up. If all of these kids are little a, we know they could get one little a from mom. Where does the other one have to come from? Has to come from dad. So we know that dad over here is big A, little a. He's heterozygous. And we can do the same for our other parents. This dad has to be heterozygous, big A, little a, because over here we've got kids who got little a from mom. They got their other little a had to come from dad. And then on this side, A dash. Why don't we know? Because both parents are heterozygous, it's possible that those children are big A, homozygous dominant, or heterozygous, big A. We don't know. They haven't had any kids. We can't track it. We have no other information. So we're going to write A dash for both of these girls. And then over here, we've got dad, who's little a. We have this parent, this mom, who's big A dash, and we don't know about this kid, do we? We know that they are big A, and then actually we do know the second allele because the second allele has to be little a because that's what they had to get from dad. So I would change that instead of A dash. That would be big A, little a, heterozygous. Okay, take a moment, pause, go through this one more time. Remember that with a dominant trait, you're flipping everything because dominant traits are passed on in every generation. If you have the trait, you're going to probably be passing it on to your offspring. It doesn't hide, it doesn't skip generations. Let's look at another example here. I'll move this out of the way again. So our first question for our third example here is, does it occur equally in males and females? And if you look, the answer is no, definitely doesn't. The only ones who are getting it are males. So that tells us that this is sex-linked. We're going to need to remember our sex chromosomes. XX for a female, XY for a male. And it tells us here that all affected males, are 3 shaded in boxes here, are going to be X little a Y. So we're going to start building our pedigree, start writing those in with the males being X little a Y. And all of the females are going to just be XX. Now hang with me. I know this looks crazy and it looks like it's going to be a ton of work to do, but it's actually not so bad. One quick tip is with X-linked traits, if a guy has something, he can blame his mother. It's not his dad's fault. So guys, this is your permission. If you have any X-linked traits, blame your mama. It's always her fault. Okay, so it's mama's fault if this guy has color blindness. It's mama's fault if this guy has um, early baldness or hemophilia or muscular dystrophy. All of those are X-linked recessive disorders. And if a guy has it, it had to come from his mom because his Y chromosome came from dad. So it's always that mom's fault if a boy has an X-linked disorder. So knowing that and knowing that mom doesn't have the trait, that tells me that mom has to be a carrier. She doesn't look like she's got it, but it's hiding on that second X chromosome and she's probably going to pass it along. So we're going to shade her in as a carrier. X big A, she's not sick. X little a, she was still able to pass it on to her sons. And we would do that for any male. So this guy has it. Who does he blame? Blame his mother. She's a carrier. How did she get it? It's because she got a good X capital A from her mom, but she had to get an X little a from her dad. So in the case where a father has an X-linked disorder, all of his daughters are going to be carriers. Okay, so this guy here, we didn't fill it out for him, but we showed that one daughter is a carrier. This daughter would also have to be a carrier for this disorder. Because girls, you get one X chromosome from mom, one X chromosome from dad. That's all you'd have to do to solve these X-linked disorders. Once you figure out that it's X-linked and that all affected males are X little a.y, you simply remember the tip. Guys blame their mothers. So mom has to be a carrier. Here's this guy. His mom has to be a carrier. Where did she get it from? She got that X little a from dad. That's why she's a carrier. The X big A from mom means that she didn't actually get sick with this trait.